গুড মর্নিং গাইস। সো আজকে তো শুভ নববর্ষ, বাংলায় প্রথমে বলে নিচ্ছি, শুভ নববর্ষ সকলকে। সবাই সাবধানে থাকবে। যে কন্ডিশনটা এখন চলছে, দ্য কন্ডিশন ইজ নট টু গুড। ওকে, সো স্টে হোম, স্টে সেফ। সবাই ভালো থেকো। নববর্ষের দিন সবাই আমরা আনন্দে কাটাই, বাট এই বছরটা একটু ডিফারেন্ট হলো, কিছু করার নেই। সো সবাই বাড়িতে থেকো। So let's start our class for today. Yesterday, in the last class, we have discussed the most interesting and one of the most toughest topic of steel design, that is the design of a plate girder. So, as we have designed the plate girder, now it comes to an example. So, we have seen how a plate girder is designed. We have seen the design topics. We have seen how the design topics and proceeds are done with the help of IS 800. We have seen all the steps, the design of the wave plate, the design of the flange plate. Then we have designed the stiffeners, end bearing, as well as the transverse. Then we have seen the torsional requirement and the connection, weld connection. So all the steps we have discussed. Now comes the most important part, one of the math we will show. We will see how a math is being done with the help of the steps that I have discussed and with the help of IS 800. So for today our lecture will be based on the math that we will see. Okay, so today we will do one math. Now let us open the math, which is very much also important for our exam also. So the math says design a welded plate girder, 24 meter in span and laterally restrained throughout. It has to support a uniform load of 100 kilonewton per meter throughout the span exclusive of self weight. So it is the only load that is acting. Design the girder with intermediate stiffener. It has been specified here with intermediate transverse stiffener. So we have to design the girder with the help of intermediate transverse stiffener. So it has been said there. Steel for flange and wave plate is 8400, that is also given. Design the plate girder and the stiffener. So we have to design the plate girder and the stiffener and the connection also. So let us proceed with the steps. So let us open another window for our design steps. I think the design step is that. Okay, first let us open the design steps that we will proceed now. First, the step number 1 is, so first we have written all the things that given to us. Now coming to the step number 1. What does step number 1 says? It's basically an empirical formula to calculate the self weight, W by 200 to W by 400. Let us assume, so we have assumed the self weight of the girder W by 300. In between that, so first W is calculated. W by formula, that formula we have to calculate the W. That formula, using that formula, you have to calculate the W. 1.5 W dash into L. So 1.5 W dash into L, using that formula you have to calculate the capital W. So let us W dash applied load in kilonewton per meter. So W equals to will be 1.5 W dash. So putting the value of 100 here. So self weight will be equals to putting the value, all the values here. 1.5 is the load factor, coming to 12 kilonewton per meter is the value of the self weight of the that acting on the plate girder. Now total factored load will be W self weight plus 1.5 into the W dash is the factored load. So 12 plus 1.5 into 100, that is 162 kilonewton per meter. So the load is 162 kilonewton per meter. That is the load acting on the plate girder. So the load calculation is complete by this formula. Now coming to the second formula, that is step number 2. What is step number 2 says? Determination of the bending moment and shear force. So as it's a beam where only this UDL is acting, the self weight as well as the total load is acting as a UDL, uniformly distributed load. Say here it is said 100 kilonewton per meter. We have also calculated the value of the load 100 kilonewton per meter. So 100 kilonewton per meter means uniformly distributed load. So for that we have to use the maximum bending moment formula, WL square by 8 and WL by 2. So putting all the value here, we are getting 1944 kilonewton per meter, 1944 kilonewton. Sorry, there will be one there has been a mistake. shear force is always in kilonewton. So 1944 kilonewton is the value of the shear force, and bending moment has the value of 11664 kilonewton meter. So two values are there, maximum bending moment and maximum shear force we have calculated. Now coming to the design of the plate girder. First, so design of the plate girder, now we are starting with the depth of the wave. So we have first we will do the depth of the wave. So depth of the wave says the optimum depth for the plate girder is that formula by calculation. So putting the value optimum depth of the plate girder, D is equal to mz into k by fy by root to the power 0.33. Now we have to assume the value of k. K is assumed in the range of 135 to 240 in between the values. Now here I have also said that the value of the k should be taken in a lower side, because if the value of the k is in lower side, the value of the d will be in lower side. So if the value of the d will be in lower side, so the wave depth will be lower, so the buckling of the wave will be less. So the value of the k has to be taken in a lower side. So always the k is assumed in a lower side so that the depth becomes smaller. So we are assuming the KL in 170 millimeter, that is the value of the k we are assuming. Now here it is said that the transverse stiffener will be used. Okay, so when we are going for that all criteria, we have to take this criteria: serviceability requirement for transverse wave with stiffeners. Okay, transverse wave with stiffeners, that criteria we have to check. Now we will check the criteria in the later stage, in the step number 3 we will check that. When we are determining the shear strength of the girder, we will check the criteria. Okay, now we need to value of the d. We are getting the value of the d from the optimum depth. So putting the value of the d is equal to, so putting the value of the d in this formula, fy into k by fy. So putting the value here, we are getting optimum depth equals to mz value we have got 11664, k value we have assumed 170, and fy we know 250. So putting the value 1848.36. So 1900 mm is the depth of the wave we are getting. Clear? So depth of the wave we are completed with that formula. Now coming to the thickness of the wave. Thickness of the wave is also calculated from that formula. Here it is given, that formula, mz by fy into k square. So putting the values here, mz by fy into k square, it is coming 7.316. Taking a value, taking a round figure, it is coming 10. We are assuming the value of 10. Okay, it is some higher value than that. So providing wave plate value is 1900 into 10 mm. So 1900 is the depth of the wave and 10 is the thickness of the wave. So that part is covered. Part number B. Now third part is the design of the flange plate. So flange plate formula is that formula, mz gamma mw fy by d. We are getting 27,011.37 millimeter square. This is the total area of the flange plate. Now what is that? How the thing is calculated? So for non-composite plate and for composite plate. So for composite, non-composite plate, ratio of width of flange to the depth of wave is taken 0.3. So width of flange to depth of wave. So that ratio is taken 0.3. So we are taking the value. From here the BF is calculated 570 mm. 570 mm is the value calculated of the BF, that is the width of the flange. So width of the flange we have calculated. So if we know the width of the flange, the thickness of the flange is calculated by the following formula: AF by BF, that is equals to 50 mm. 47.38 we are taking the value of 50 mm. So we have got the section for the plate girder. We have got the wave, we have got the flange. So let us draw the section first here. Oh, I have drawn the section here. So providing flange plate, that formula. So this is the section of the plate girder we are getting. The flange plate and the wave plate. So flange and wave we have completed the design. The first 2 steps are done. Next, coming to step number 4, section classification. We have to classify the flange plate based on that. So section classification is done for B by TF should be less than 9.4 epsilon for rolled and welded. As it is a welded plate girder, it should be less than 8.4 epsilon. We need to check that. So B by TF. What is the meaning of B? B means from here to here. This is B. B is calculated by BF minus TF by 2, that we know here. So BF minus TF by 2 divided by TF, we are getting 5.2. It is less than 8.4 epsilon because epsilon for Fe250 is equal to 1. So hence it's a plastic section. So always try to provide a plastic section. So we are getting a plastic section as required. So step number 4 is done. Now coming to the step number 5, moment capacity. So the moment capacity is calculated by the clause number 8.2.1.2. So first we have to calculate the moment capacity. So beta B ZPFY by gamma M0. Beta B 1.0 for plastic and compact, so putting the value of 1.0 for plastic and compact, ZP we have to calculate. Plastic section modulus of flange plate only. So this flange plate and this flange plate, the plastic section modulus we have to calculate. So ZP we have to determine. So what is the formula for calculating ZP? I have shown you. This is the formula for calculating the ZP, that is the plastic section modulus. So ZP is calculated based on that formula. This is the value. Putting all the values, capital D we know. Now what is the capital D? The overall depth, that is from here to here. So overall depth equals to 1900 plus 2 into 50, because 50 is the depth of the flange. So putting all the values, we are getting 55.58 into 10 to the power 6 Newton millimeter square. That is the value of the ZP we are getting. So MD, putting the value of all the ZP, Fy, gamma M0, we are getting 12,631.82 kilonewton per meter, which is greater than the MZ value. What the value of MZ we have got? 11,664. So moment capacity is safe in the design. Okay, but as we know, the most important problem for the design of plate girder is the most important problem for the design of the plate girder is the shear capacity, that is the buckling we have to check. So let us check the shear capacity. Now the shear capacity, for checking the shear capacity, as we are determining the shear capacity, we need the value of C, that is the C value, that is the spacing we need to find out, because here if we are using any formula, simple post critical method or tension field method, we need the value of the spacing. So spacing is calculated. How it is done? Basically, so first assume a C by D ratio between 1.2 to 1.6. So let us assume a C by D ratio 1.4. In between that we are assuming. So 1.4 we are assuming. From here C is calculated 2660 meter is the value of the spacing between the two waves. Now we have to check for serviceability criteria. Now what the value we are getting from the serviceability requirement we have to check. Now serviceability requirement for wave with stiffener, that is we are assuming that the wave is with stiffener. So let us check the value. Now this criteria we are getting. Why? Now if we see okay, stop here. Okay, now if you see only this criteria is getting fulfilled, that is 3D, that is 3 into the dimension 3D, that is 5700, because D is 1900. So 3D is equal to 5700. It is less than, so 3D greater than C, that means 3D greater than C greater than C less than 3D. C value is 2600, which is less than 5700, and C also greater than D. D means 19,000. So 1900. So this criteria is fulfilled. So as this criteria is fulfilled, D by TW should be less than 200 epsilon. So we are getting the value of 2 by epsilon here. And for flange buckling criteria, for flange buckling requirement, when C greater than 1.5 D, so C here is less than 1.5 D, because 1.5 into D is more than 2660. So also C is getting here the value of that C. So D by TW we are getting 345 epsilon F. So all this criteria is done. So D by TW we are getting 190, which is less than that. So therefore this criteria is satisfied. So this criteria is satisfied, that means their criteria for the shear check first criteria is satisfied. Now here only transverse stiffeners will be provided. So transverse stiffeners is required, only transverse stiffeners. So let us calculate the spacing of the transverse stiffeners. How many panels will be created? What is the panel? I think you basically know that if this is the one stiffener transverse, if this is another stiffener, if in there is another stiffener, so this is the distance between this is called a panel. It is a panel. Okay, it is one panel. So there will be numbers of panel. How many is the length divided by the spacing? That will be the number of the panel created. So number of the panels formed by the stiffener 9.02. We are taking 9 knots. 9 numbers of panels are forming with the help of that stiffener. So panels dimension, number of panels we have determined. Now we have to check for the shear capacity. There are two formulas basically, you know. Number one is simple post critical method. The second one is tension field method. As it is not specified in the math, that is what formula we have to use. Basically we will use simple post critical method basically. So using the simple post critical method, the formula is given here as well as in the code. So Vn equals to VCR, the VCR is equal to will be AV into tau B, AB is equal to shear area D into TW. That is the value we are getting from the code. So putting all the value here, D into TW into tau B. So now for CD, see by now how to calculate the value of the tau B. So tau B depending on all the values. So first we have to calculate the kV value. kV, so C by D ratio we are getting 1.4, which is less than 1.0. So we have to use that formula. So putting the values in that formula, we are getting kV is equal to 7.39. So now the tau CR comma C, elastic critical shear stress of wave, have to calculate it by that formula. Taking mu is equal to 0.3 Poisson's ratio, putting all the values here, we are getting 37.00 kilonewton per millimeter square. Then we have to calculate the value of the tau B. So we are getting the tau CRC, now we are getting the lambda W. Lambda W formula is that, so lambda W we are getting 1.98, putting all the values are here. Now lambda W here is 1.98, that means it is greater than 1.2. So we have to use that formula of tau B, FYW by root over 3 gamma MW square. So putting all the values, we are getting 36.82 Newton per millimeter square. So putting the value of the tau B in that equation, D into T into tau W, so we are getting 699.58 Newton, which is less than the Vz. That means there will be requirement of transverse stiffeners. That means intermediate transverse stiffeners will be required, as we are getting the value of the shear capacity less than the shear force acting. So transverse stiffeners has to be provided. Okay, so this check is also done. Now coming to the check number, step number 7. What does the step number 7 says? Now you can also try the tension field method. You will get another value of the shear. So either tension field method or simple post critical method we can use. Now coming to the step number 7, end bearing stiffener. That is the end bearing. That is the stiffener that is present at the end of the plate girder, so as to resist the shear force acting. So end bearing stiffener we have to design. So first the local capacity is calculated, Fw divided by B1 plus N2 into Tw into Fyw by gamma m0. Now as there is absence of the value of B1, we are taking the value of B1 equals to 100, that is says here. So B1 equals to 100 we are taking, B1 equals to 100 mm. So N2, using that formula we are getting N2 equals to 125 mm. So Fw will be equals to that formula. So putting all the values here, B1 into Fy, that value, Fw is equal to that value, we are getting 511.36 kilonewton, which is also less than the Vz, that is the 1944. So there will be requirement of the end bearing stiffener, that I have told you always in case of the plate girder design. Fw value is as the Fw value is always much more less, so it is always less than Vz value. So end bearing stiffeners will be provided. End bearing stiffeners will be provided. Now the first we have to calculate the bearing area. How the bearing area is calculated? Using the clause 8.7.5.2. This is the AQ, that is the area of the bearing of the transverse stiffener. So this is the area AQ of the bearing area of the transverse stiffeners. We have to calculate. We are getting 6842.88 millimeter square. Now always in the bearing stiffener we have to take two plates, two bearing stiffener at the each end of the wave. So if this is the wave, there will be one bearing stiffener, there will be another bearing stiffener. So two bearing stiffener is always provided. Okay, so let us provide two NOS ISF 200 into 210 into 25 mm. So 210 mm into 25 mm. Now let us clarify something. I have checked this math also with the help of 200 into 20, but in the lateral torsional buckling criteria, that stiffener fails. So I am assuming a higher value. In the exam, if you got some problems in the lateral torsional buckling, simply says that the design need to be revised. Okay, you don't need to redesign that thing. That's right. The design need to be revised. Okay, so I am taking here the ISF 210 into 25 mm as the bearing stiffener as both sides of the wave. Okay, so 210 into 25 mm. So that is the length of the, so width is 210 and thickness of the plate is 25 that we are getting. So total area provided will be equals to 200 into 10, 25 into 2, because two areas are there, two bearing stiffeners, two plates. So total area is 8000 we are providing. So it is less than 6842. So 10,500 millimeter square we are getting, which is much more higher than the value required. So this criteria is satisfied. Now coming to the next criteria, that is the check for outstand of stiffener. So outstand of the stiffener we have to check. Okay, so outstand of the stiffener is checked. The outstand of the stiffener BS shall not exceed that two values. So what is the value of the BS we are getting? BS means the width of the stiffener plate. So width of the stiffener plate we have provided is 210 mm. So let us check it is if it is less than that two values. So 200 into 2, that is equals to 400, and that is equals to 280. So that value is, that criteria is also satisfied. So check for the outstand of the stiffener is also satisfied. Now coming to the check for the buckling of the stiffener, that is the important portion. So here it is TSP, that is the thickness of the stiffener plate, BS is the outstand length, TW is the width of the web. Now area effective, that I have told you, when the bearing stiffener as well as the web is acting as a unit, this portion will act as a column when in the case of buckling of the stiffener. So that the area that will be effective against the buckling will be this total area that I have told you in the previous class. So that area we have to calculate. So from the center line of the stiffener to the end point of the area, is it 20 into TW? So for two numbers there will be 2 into 2 into TW, that formula. So putting the value of the A effective here, we are getting 14,500 millimeter square, which is a very high value. So A effective we are getting. Now IXX for the stiffener are determined with respect to the center line of the web. Why the center line of the web? You know that because as two stiffeners are provided, there will be two numbers. The IXX of the stiffener plate will be calculated as per the center line of the wave. We have to calculate the as per the center line of the wave. So we have to use the formula for the what is that? The formula for the parallaxis theorem. So for that plate and that plate, so two numbers of stiffener plates are there. So now two numbers. What is the area? First we have to calculate the moment of inertia of that area, then we have to calculate from this center distance to that center distance, we have to AH square. So IXX plus AH square we have to calculate. So putting all the values here, TSP into BS cube by 12 plus area into H. So H means BS by 2 plus the thickness of the wave by 2. So putting all the values here, we are getting that value 156.64 into 10 to the power 6 millimeter to the power 4. That is the value of the IXX. So now R will be equals to IXX by A effective, that is equals to R value. So for R, now KL, K means the value of the slenderness ratio factor. So effective length factor is 0.7 because all that position are restrained. So we are taking 0.7. So 12.44 we are getting. Now for KL by 4, 12.44, FY 250 and buckling class C from 9.C. Let us open the code 9.C IS 800. So this is IS 800. Let us move to 8. Okay, so this is the table number 9C. Let us find, okay, 9A, 9B, 9C. Okay. So this is the 9C table. From here for KL by R ratio 12.54. So it will be in between that value, and for FY 250. So if we move from here to here, our cursor, we will see the value will come between these two values. We have to interpolate those things. So by interpolating, we are getting 226.27 Newton per millimeter square. So putting the value of the 227.27, we are getting PD equals to 3280.9, which is much more higher than the 1944. So the stiffening criteria, the bearing stiffener criteria is satisfied. So this is the design of the bearing stiffener. So this part is complete. Very much, please make yourself clear about the calculation of the IXX. Why we are determining the IXX as per the center line. Please make yourself clear about that. Why we are determining the IXX in the middle of the wave. We are taking the neutral axis at the middle of the wave because two number of plates are there. If there will be one plate in one side, so there the center line, the CG distance will be taken at the face of the wave, that we know. So let us go to the next step, that is the step number 8, intermediate bearing stiffener calculation. So let us take the intermediate bearing stiffener. So here first the spacing of the transverse stiffener by the depth of the wave is determined. So spacing of the transverse stiffener we know that is equal to 2660, and depth of the wave is equal to 1900 400. So 1.2. So it is less than. So C by D ratio is less than root over 2. What is the value of root over 2? Root over 2 means 1.41. So it is less than root over 2. So this formula will be used. So using this formula, the required MI is 141.41 into 10 to the power 4. So let us provide one plate, either one plate or two plate, to carry over this moment of inertia. So providing intermediate stiffener of ISF 100 into 8, because the moment of inertia is much more less, we will only use 100 into 8 mm on both sides. So there will be two number of wave in each side of the wave plate. Okay, so two numbers. So here also the IXX will be calculated at the center line of the wave, because two numbers of intermediate stiffener we are providing in the each face of the wave. So IS to be calculated at the center of the wave. So first IS to be calculated. Now, so IS will be equal to at the center line of the wave. So using the center line, all right. So here this formula will again be replied. Okay, this formula will again be replied. So putting this formula, TSP into BSS cube by 2A plus the area into that distance from here to here, that is the BS by 2 plus BSTW by 2, that distance we have to take. So putting all the values here, we are getting 617.33 into 10 to the power 4 millimeter square, which is much more higher than the 145.41. So this criteria is satisfied. So we can proceed with that plate of our requirement. So then we have to check for the buckling of the stiffeners. Oh sorry, check for the outstand. First check for the outstand. Same criteria we have to check. So let us, as we are BS 100 mm, which is less than 160 and 112. So hence it is okay. TQ is equal to the thickness of the stiffener that we know, it is 8 mm. So we are getting all the values. So 112 and 160. So this criteria is satisfied. Now coming to the check for the buckling of the stiffener. How the check is done for the buckling of the stiffener? Using this formula. FQ is equal to V minus VCR by gamma M0. So in our math we have calculated the VCR, that I know. VCR equals to, we have calculated, what is the value of the VCR? 699.58. So you will use that value here also. So 699.58 we are taking the VCR. Now V is equal to, yes, calculated. You know what is the V? That is the share at the adjacent stiffener, which is calculated by that formula. So putting all the values here, L minus L is equal to 24,000. That is the total length, minus C is the spacing. We are getting 1728.54 kilonewton. That is the V, that is the shear force acting on the adjacent stiffener. So putting all the values of here, FQ is equal to 109692.56 kilonewton. So the buckling, so the what is that? The compressive strength, the design compressive strength of the stiffener should be higher than that FQ value. Let us check that. So area effective, that is the area effective, as the similar case here it is calculated as that value, because area effective is like that. So we are using that effective area. So putting all the values here, we are getting 5600 millimeter square. IXX, as per the center line of the wave, we have calculated here, that is 617.33 10 to the power 4 millimeter square. So putting as determined from the stiffener plate on the both sides. So putting R is equal to IXX, that is value. So A lambda is equal to KL by R, 0.7, as both sides is restrained, we are getting 40.06. Now let us come to that load also. So 40.06 and Fy is equal to 250, Fy equals to 250 MPa and buckling class C here also, because solid place is there. From table number 9C we are getting Fc is equal to 197. Let us check. So 40 and 50. So that two values, that means these two values will be there, 198, okay, let us zoom in, 198 and 183, we are taking 197.32, which is somehow less than that because it is 30.0406. So putting PD is equal to that value, we are getting 1104.92. So this criteria is also satisfied. So the design of the intermediate as well as the bearing stiffener is done. So we have done all the design part of our map. So designing portion is done. Let us design the connection now. So so connection will be there, the design of the connection will be there. So first the flange to wave connection, the design of the flange to wave connection we have to check. Okay, so first let us check the connection part. What is the first connection to be checked? That is equals to step number 9, flange to wave connection. So first the QW, that is the shear force coming to the weld between the wave and the flange, it is the value of that value, where Iz is equal to the moment of inertia of the whole section about that axis. So calculating the moment of inertia of the whole section about that axis. So let us find the area 599.13.30.10 to the power 6, because that two portion is the flange portion. So here will be the use of parallel axis theorem, and as this wave portion, the CG is passing through the center line, there is no requirement. So putting all the values here, we are getting Izz equals to that value. Now QW we are putting okay, V is equal to, what is V? V is equal to the Vz, we know 1944. AF, area of the flange, we know that value, and Y dash equal distance of the CG of the flange from the CG of the total section. So what will be the distance of the CG of the flange to total section? So from here to here, the value is coming equals to 1900 by 2 plus 50 by 2, 975 mm, that we know. So putting all the values here, QW is calculated 0.9016 kilonewton per millimeter, that is the value we are getting, 0.9016 kilonewton per millimeter. Now we have to assume, so this amount of force is acting on the weld, so weld should be designed to resist that amount of load. So let us assume a weld size. As the load is somehow higher, we have to have assume some higher amount of weld. So let us assume the size of the weld, 12 mm size of the weld we are assuming. So TF, that is the thickness of throat thickness, which will be coming 0.7 into S, that is the formula, putting the 0.7 into S, 8.4 millimeter. So FWD per meter run. So for we are determining the FWD per meter run. So for 1 meter, what is the strength we are getting? Here also we have determined the value per meter run. So meter run will be used. So putting all the values, it is coming 0.97 kilonewton per meter, which is greater than 0.9016 kilonewton per meter. So okay, 1.25, why? Because soft welding is used. So the weld between the wave and the flange is satisfied. So it is okay, it is done. So next comes the second cut, connection between the end bearing and the stiffener with the wave plate. So end bearing stiffener with the wave plate is connected. Now first we have to assume the coping length that we that you know. So there will be, so provide the weld, some length of the coping length has to be adopted. So let us provide the coping length equals to 20 mm. So as the coping length is there, as the length has been coped, the BS, the value of the BS will also be less, because the value of the BS we are getting total BS minus that value. Okay, so dash BS dash we are getting 190 mm. Okay, 190 mm we are getting the value of the BS. So tension capacity of the flat we have to calculate from that. Tension capacity of the one flat equals to that value. We are putting all the values, 0.9 BS dash we are getting 190, TSP we know that is 50, 25 we know, FU is equal to 4110, we are putting the value 1402 kilonewton. Now shear, determining the shear per unit length, that value. So putting all the values here, we are getting 0.373 kilonewton per meter. So that shear per unit length is coming to the weld connection. We have to check if the weld is satisfied or not. We have to assume, similarly we have to assume some size of the weld. Let us assume 8 mm dia of the size of the weld. Okay, so TT, that is equals to 0.7 into 8, 5.6 mm we are calculated. So putting the value here, we are getting 1.06 kilonewton per millimeter, which is higher than the 0.373 kilonewton per millimeter. So hence it is also safe. So the weld connection that we have provided for the both connection, that is the for connection of the wave to flange and the connection of the end bearing plate to the wave, these two connections are satisfied, these two connections are okay. So we can proceed with the last portion of our design, that is the check for the torsional capacity. Now one thing I will like to say here, that when in my math, when I have done this math for you, in the torsional capacity, first in the end bearing plate, I have assumed the end bearing plate size 200 into 25. So that plate has been failed. Then I have assumed another bearing plate. So in the math exam, if in the exam, after the assuming this torsional buckling provided is the torsional stiffener, the torsional criteria is failed due to the shear buckling, we have to provide torsional stiffener also. Torsional stiffener will be designed as the similar way as the bearing stiffener, but if in the exam the time is less, you can also say the bearing stiffener, the last portion you can say the bearing stiffener will be redesigned. That portion you can also say if the time is less. Okay, so let us proceed with the criteria. So moment of the area of the end bearing stiffener about the central line of the wave should be determined. So this is the central line of the wave. So moment of area will be determined. So first the Iy, so now okay, first here we need the value of Ry, that is the least radius of gyration in the y direction. So first we have to determine the Iy of the whole section as based on the y section. So as the y section central line passes to the central line of the total section, so there will be no need of the parallaxis theorem. We can put the values here. We are getting the value 1543.4 into 10 to the power 6 millimeter to the power 4. So A equals to, so this is the value, and A equals to 550 into total area, that total area BF into TA plus 2 into BF into TA plus D into TW, putting all the values we are getting 76,000. So Ry we are getting 142.51. Now LLT, that is the LLT. So LLT will be LLT, that is the effective length from the table number 15. So what value to take? Table number 15 of IS 800. Let us go for table number IS 800. Let us go. Table number 15. Okay, so table number 15, I think it is here. Okay, so table number 15 says what value you have to take for fully restrained case, warping case. This is the case of warping, because we are determining the torsional resistance due to the torsion is twisting, warping of the plate occurs. There is twisting moment. Okay, so as the torsional criteria we are determining, so the warping case we have to take. So for fully restrained, we have to take 1.00 L for a normal loading condition. So we are taking the value of the K is equal to 1.0. So L is equal, LL2 is equal to same value, that is equal to 24,000 millimeter. 24,000 millimeter, that is the same value. So LLT by Ry we are getting 168.41. So LLT by Ry, so depending on the LLT by Ry we have to take the value. So LLT by Ry we are getting 1868. So that value, of the alpha x we have to take. So alpha x equals to, putting all the values here, we are getting 10.58 into 10 to the power minus 4. Now we have to put the value here 0.34 into alpha x into d cube by TEF. So d is equal to the total overall depth 2 into 50, 2000 millimeter. TEF is the thickness of the flange 50. So IS provided that the IS is provided. The IS means moment of inertia of the bearing stiffener of the wave. That means at the central line of the wave we have to calculate the bearing stiffener. So putting the values here, we are getting 165.64. We have calculated that here also, same value we have calculated here also in the case of bearing stiffener. So we have getting 165.64, the same value we are getting. So putting the value here 165.64, we are writing the value, same value here, it is greater than that value 143.88. Putting all the values in this formula, we are getting the value here also. So that torsional criteria is also satisfied. So this is the end of the design criteria. So in the total design example, we have seen how the math is being done. Very important, very interesting math, because all the criteria are given in the code. We have to check the code, where are the formulas in the code. We have to check that first. Then you have to determine the values. So please go through that and please do the math by yourself. And in the book also there is some math extra. So please there is some examples also. Please go through that examples and do that by yourself. This is the math. So here we have seen that all the design criteria are satisfied. Now I am also telling you the last thing, that is, if the torsional buckling criteria, I have told you many times before, that the torsional buckling criteria at the end is not satisfied, please write the end bearing has to be redesigned. Okay, so this is the math. If you do the math, you will get 15 marks sure. Please exercise the math and do that math very carefully. Okay, শুভ নববর্ষ সকলকে, সবাইকে শেষে জানাই, অ্যান্ড থ্যাংকস টু ইউ। ওকে, গুড বাই ফর টুডে। থ্যাংক ইউ ভেরি মাচ ক্লাস।